Let us start. Hello, am I audible now? Hello.
Yes, sir.
Now, let us go through this simply supported beam of 7 meter span with overhang rads on supports which are 4 meter apart. And left end overhang is 2, and the beam carries a load of 30 kilonewton, 20 kilonewton on the left end and right end respectively, away from a uniformly distributed load 25 kN between the supporting points. So please draw shear force and bending moment diagrams. So what is given in the problem is it is total span length is 7 meter, which is given as 2 plus 4 plus 1 is equal to 7 meter span length. And one load of 30 kilonewton is loaded at the point C, which is the extreme left point. It is being supported at the point A, at the point B, and the left hand support is 2 meter away from the end, and in between there is 4 meter length, and right hand support is 1 meter. And it is carrying another single vertical load of value 20 kilonewton at the right end B. Besides these two loads, 30 kilonewton and 20 kilonewton, we are having a uniformly distributed load of 25 kilonewton starting from the support point A and finishing at the support point B. So there are three forces: 30 kN, 40 kN, 25 kN, and being supported at A and B. So you have to find out SFD, shear force diagram, and BMD. We have already done the shear forces. Just have mentioned you the sign convention again. So if we take a section here, somewhere here, and if the bending moment is, if the resultant bending moment is acting upward, then shear force will be positive. But here resultant, but there is only one moment acting, that is also acting downward, that is say 30 kilonewton. So shear force will be equal to 30 kilonewton, but equal to 30 K negative, but it's negative in nature. Next, we take a section here at a distance x from the left end. So what will happen? Oh, first of all, we have calculated the reaction at A and at reaction at B. So by taking the moments about B, so RA reaction at A becomes 90 K and RB reaction at B is equal to 60 K. Both are acting upwards and pointed in nature. Now, if we take second section at a distance x away from C, so what will happen? The shear force will be positive. One force is acting downwards, that is minus 30 K, and reaction is acting upwards, that should be positive, as it should be as per our sign combination, that is 90, and minus x minus, that is x minus 2 multiplied by 25 is another force which is also acting at the middle of this distributed force, that is acting downwards. So it should be negative in nature. So this 30 is negative, it is acting downwards. As per sign convention, it will be positive only when it is acting upwards. 90 is reaction acting upwards, so it is positive. And 25x is the resultant of the distribution force, which is also acting downwards, so it's negative. Thus, shear force Fx is minus 30 plus 90 minus 25x, or 60 minus 25x minus 2. That should be 25x, not exactly 25, but x minus 2. Achha. So Fx is 60 kilonewton. If we put x is equal to 0, means x is equal to here 0, then Fx is equal to 2, means at a distance x is equal to 60 kilonewton. It is equal to x, so this portion will become 0. This FA, shear force at A, is the 60 kilonewton positive. And at the point B here, where x is equal to 2 plus 4, 6. So if we put 6 here, it will 4 means 100, minus 25 into 4 means minus 100. 60 minus 100 means minus 40. Here, the shear force is negative in nature at the point 2. So at the point 4, this is negative, this is point side, this is negative, and become equal to 40. And at the point A, it is become positive, and this is become positive itself. Now, if we take the section again here, so here the shear force, it will have two vertical sections for here at A and at B, factorial upwards, which is positive, and one negative side force 30 kilonewton, which is acting downwards, and another negative 25 into 4, 100 kilonewton, which is also acting downwards. So what we hope portion at PD, that is minus 60 plus 60, is equal to 60 kilonewton. It is equal to minus 30 minus 100 plus 60. RA is 90 plus 60 plus 90 plus 60. Means this is 150, this is minus 130. That is 150 minus 130 is 20 kilonewton. So this is shown in the figure here. So this is the shear force diagram: 30 kilonewton, 60 kilonewton, and 40 kilonewton. Now, let us go through the bending moment diagram. Here, if we take a section here, as initially we have taken, and find out what is the clockwise bending moment here, then there's only one force acting here, that is 30 kilonewton at a distance x, that is 30 into x. It is also anti-clockwise in nature, so it is negative or minus 30x linear. And so if x is equal to 0, bending moment is 0 here, and if x is equal to 2, means x is equal to at the point 2, the bending moment will be equal to minus 60 kilonewton. So here we draw the bending moment as it is linearly varying from 0 to 60. So it is minus in nature, minus 60 into kilonewton, minus 60 kilonewton. Then the portion AB, say force is there, 30 kilonewton here, and reaction 90 kilonewton here. In the clock, it is making the 30 kilonewton force, which is making anti-clockwise moment from the moment from, if we take the moment from the section, so it will be negative, that is minus 30x, and 90 kN force, which is at a distance, acting at a distance x minus 2 from the section, it will be positive because it is clearly positive clockwise bending moment. So if we add them, 90 x minus 2 and minus 30x. So next is coming the distributed forces ranging from x minus 2. So the distributed will be rate of distribution 25. The force involved is 25 into x, and the distance of acting is the force is exactly the center. So that distance will be x minus 2 divided by 2. So as this is creating an anti-clockwise bending moment, which is negative in nature, so this is becomes minus 25x minus 2 whole square by 2. So this is a parabolic in nature. And if we put x is equal to 2, means at the point A, it will be equal to minus 60 kilonewton. Means this is 60, this is 0, this is also 0. So minus 60 kilonewton is the bending moment at the point 2. So we are having the same bending moment here, which I have already calculated in our earlier calculation. Then bending moment will be maximum at 4.4 and 60, and bending moment is x is equal to 6, means bending moment at the point B is given as 130 minus multiplied by 6 means 180. X minus 6 minus 2 is equal to 4, that is 360, minus x minus 2, that is 4, 416, 25 into 16 divided by 2, 2 means 8 means 200. So that is goes up to 380 plus 250. 380 plus 200 means 380 minus 380 plus 360 means equal to minus 20 kilonewton at the point D. Now, what should be the maximum bending moment? It is supposed to be 4.4. 4. Yes. The bending moment which is equal to 0 uh, is maximum supposed to be maximum at 5.5. If we make it bending moment at maximum 4.5 is 5.5. Bending moment is 0 at 30 minus x minus 90 xx to 25 into x by 2 whole squared by 2 is equal to 0. If we simplify the equation will become 12.5 x square minus 120x plus 230 equal to 0. So x will be by equation minus b plus minus square root of b square minus 4ac by 2a, where a is to 12.5, b is 110, minus means positive, and c is equal to 230. If we make the calculation, we will get x is equal to 5.23 and 3.42, where bending moment is equal to 0, which means bending moment curve is intersecting at this section here and at this section here. And one is 3.42 and another is 5.42. And if we take the derivative of bending moment in terms of x and equal to 0, we'll find that bending moment will be maximum at the point 4.4. And it will be equal to 5.5 kilonewton per minute. Here, this bending moment curve is maximum at 5.5, otherwise it is less or more from this point to this point. The portion BD means right end of the bending, right side end of the bending moment is equal to, that is 1 minus 30, which is creating anti-clockwise bending moment, plus reaction 90 minus x minus 2, which is creating clockwise bending moment. And 25 multiplied by 4 into x minus 4, that is the distributed force acting over the beam, and plus, which is creating anti-clockwise bending moment, so it is negative, plus 60 into 4, that is the reaction at B, which is creating clockwise bending moment, which is x minus 6. As x is taken here, and this distance from here to here is equal to 6. So, MBX, when x is equal to 6, then the bending moment will be the minus 20, because this portion will become 0, this portion is 2. 2 into 2, 8 means minus 200. 6 into 4, 36 multiplied by 6, that is becomes minus 20 kilonewton per minute. And d is equal to 7, x is equal to 7, this bending moment will be equal to 0. Means x is equal to 7 is the distance here, 2 plus 3 hand. X is equal to 7, then the bending moment is supposed to be equal to 0. So let's go for the next problem. Now, a simply supported beam of length L carries a uniformly distributed load over L unit length, and it has movable support and equal overrun on either side. The supports are to be adjusted that the maximum bending moment is the minimum possible. Determine the position of the supports. Also, draw the shear force bending moment diagram. So, what is given here? First of all, it is simply supported beam. It is loaded by a uniformly distributed load, which is intensity is given as W per unit length. it has movable supports, maybe simply supported but movable, and equal overhang on both the sides. Both sides is overhanging and of equal amount. The supports have to be so adjusted that the maximum bending moment is the minimum possible. The determine the position of the supports, also draw the shear force bending moment diagram. So in what position support, the maximum moment is the minimum possible. So how will you calculate this problem? Maximum bonding moment is minimum possible. So what is given? Let us examine one by one another. It is supposed to have equal overhang. So here the support should be at A and at that B, and at from both the end A and B is equal. It is equal to small a. It is loaded from left hand to right hand by uniformly distributed load of intensity W, and it is supported at A and at B with equal to RA into RB. So we have to find out the maximum bending moment to be least, and shear force of bending moment diagram we are supposed to draw. Overhangs are small, therefore sagging moment in the middle span and hogging bending moment over the support. The maximum bending moment will be minimum if the magnitude of the maximum bending moment will be the minimum if the magnitude of the sagging and the hogging bending moment. Magnitude of the sagging and the hogging bending moments are equal. Let the overhangings on each of the length A. Length is equal to A. The RA is equal to RB is equal to W to L by 2. The position of the supports can be obtained by equating sagging and bending moments. Exactly, sagging moment at the center is equal to bending moment of the supports. So we have to follow it accordingly. Now, what is the sagging moment? First of all, L by 2 W into L by 2, because here both the supports are given as W into L by 2. So the sagging bending moment at the center, if you take a section here at the center, what will happen? The W into L by 2 multiplied by total L by 4. Means here the bend that is A, notes the same L minus A. W into L by 2. Yes, right. So here, what is going on is L by 2 is the half of the length multiplied by omega. So L by 2 nearby omega multiplied by L, it is a half of this portion from here to here is L by 2. So half of the portion will be here equal to L by 4. So from the section C, L by 4, WL by 2 is the load multiplied by the distance which is acting half of this length, which is equal to L by 4. And another force is there, that is RA, W into L by 2, which is distance is W into L by 2 minus A, which is positive as because it is creating clockwise bending moment. And this is equal to the W into A square divided by 2. So what is the W into A, the length, distance of this length multiplied by the distance A. This is A, which is half of them, and W A square divided by 2. L square minus, so if we reduce further, simplify further, it will become L square minus 4A, 4LA is equal to A square, 4A square. Or L square, L minus 2A, L square minus 4LA plus 4A square is equal to 4A square into A square. Thus, L minus 2A whole square is equal to 8A square, and L is equal to 0.28 0.828 A is plus 2A, and thus L is become 0.207. Means the sagging bending moment will be around 20% of the total length of the beam. And the bending moment here will be, if we put the value of maximum height, value of maximum sagging. So if we put it, we'll have W.00 0.07 L by 2 or 0.214 W square. Now, shear force diagram will be like this. The portion dA means a portion from N to the A. If we take a section, we'll have the W into X is the length, which is the vertical force acting over it, but it is acting downward, so it is negative, and it is become minus WX. FD is equal to 0, FA is equal to minus WA. FA is equal to minus WA and equal to minus W multiplied by 0.027 L. Equal to 0.027 L. At T is equal to 0,